And the next talk will be Dr. Rue for pores. What are they good for?
All right, hello everyone. I think you're going to get very similar talks with different versions along the way in the symposium, which is actually great. I was asked to talk about pores. When I was thinking about this slide, I actually pulled this slide from a talk I gave 10 years ago at the AANS on a symposium on bone biologics, because people were coming out with their new bone grafts and bone extenders, and they had all sorts of, marketing ploys and words that they were using. But at the end of the day, when it comes to bone biology, there have been and there will always only be 3 O's: osteoconduction, things that make bone want to go and live there, the environment that makes bones thrive, like, that's the environment that's there structurally and physically. Osteoinduction, things that attract bone. Come and live here, it's a good place to live. And finally, bone cells that grow. And that's it. If anyone else is selling you something that doesn't talk about these 3 topics, they're trying to sell you something. They're just trying to sell you something, okay? The most important thing about here that we're going to talk about is osteoconductivity. And osteoconductivity are things that make bones want to grow and live there. It provides a nice environment that literally fools the bone cells into thinking, this is bone. Because what are we doing when we're trying to fuse patients? We're trying to get bone cells to go into this area that is fractured. We're trying to fake it into thinking it's a broken femur or something and trying to connect the dots together. And how do we do that? We make it look like this is what I'm supposed to do. Because the body's pretty smart. If there's something that's not supposed to be there, what does it do? It encapsulates, it's pseudoarthrosis. It says, get out of here, or it says, I need to form a joint. That's what the bone cells are trying to do. They're blind, they can't see. They're just little cells. They have to make a decision. Am I going to form a joint, or am I going to form a bone? And how do we try to encourage that? By giving it an environment or stimulating it with some sort of chemicals or biological properties to do that, because we can't make bone, right? So what exactly is porosity? I want to talk about this concept of porosity. Bone is a porous substance. Bone cells will grow through an area that is porous, and that's what allows bones to adhere to the area, to the substrate, so it'll spread. It'll allow it to grow. It'll allow it to proliferate. But it's a very complex structure that is both nano, micro, and macro. The pores themselves in the bone have a nanostructure that makes bone cells want to stick to it and grow. It's got a microstructure that allows the cells to proliferate and grow through. And it's got a macrostructure based on the pores that gives it the modulus of elasticity, the support, and the other mechanical properties. So porosity is incredibly important. Pores at a very small, 100 micrometers, have great adhesion, but bones don't grow. Pores that are big, bones like to grow into, but they don't stick very well. Pores that are too big are very bad. I mean, nothing grows. So we have a graft with a big hole in the middle. We got to put a bone extender in there, because bones aren't going to grow through a pore that's big. So pores have varying sizes as well. Real bone has an overall porosity of 55 to 80%, but that's a general term. The porosity, depending on where you're looking, is very highly variable. Real bone has micropores that encase small volumes that are arranged in large macropores. But we have tried to simplify this idea, this complex feature set, this complex biological mechanical environment, into a simple idea called porosity, which has been easily defined as pore size and overall porosity. It's just not that simple. And that's really the main point of my talk, is porosity is incredibly important. And people will say, oh, well, our graft has a pore size of 400 micrometers. And you're like, oh, that sounds good. Oh, yeah, we have an overall porosity of 85%. Well, that sounds, is that really true? It's actually not that simple, is my point. And it's a starting point, okay? Do only the pore size matter? Is it that simple? Absolutely not. Pore size affects the ability to diffuse nutrients. It turns out if your pores are too small, you can't actually get enough oxygen to the cells, and the cells can't get the waste products out, and they die. If the pores are too big, then basically you can't get enough bone to grow. They won't connect. So you actually have different pore sizes in bone. How they're interconnected is very important. How the pores, small pores, are hooked up to big pores, the actual shape of the pores, the tortuosity of the pores, in order to get channels of nutrients in and waste out, that also varies in bone. It's not that simple. The pore shape actually affects cellular behavior. We can have nano features in the pores themselves, and this is sort of like the new metal that's being nano etched. You can actually, the pores themselves have features that make bones want to stick on them. So you can actually have an inert, non-biological surface feature that can have a biological activity. That's pretty cool. And finally, overall porosity and the macro structure of those micropores affects the modulus of elasticity. So pores are incredibly important and complex, but people have tried to simplify it. So you know what? I called Cage Rage 1.0 kind of came out. I've been doing spine surgery about 20 years, okay? And when I first started coming out, we were coming out with all these cages, and I called that Cage Rage 1.0. And if you look at the history of cages, we had autografts, allografts, stainless steel. Titanium cages came out very early, but they were solid blocks of metal, okay? Basically no bones growing through that, all right? And then in the 90s, we had PEEK, and PEEK came out, and that's when Cage Rage came out. And why do we like PEEK? Good modulus of elasticity. It's not going to burn into bone, but we had to pack it with something, right? We had to come out with something to pack it because it in and of itself actually had no biological properties to make bones grow. So now in 2010, I call this 3D manufactured metals. I'll talk about that in a second. But in order to make bone grow, what we started studying were these three properties of what we're going to put into the space to make bones grow. And as you know, autograft is the best, allograft not so good, but then osteoconductive grafts came out. If you look at TCA, hydroxyapatite, and those were actually artificial structures that made bone want to grow, and they actually work to varying degrees. BMP showed that we could actually provide an osteoinductive chemical. That's one of the few things as a FDA trial data that shows that it works. You can just use that alone to make bones grow, and then you can combine things together. I think bioactive glass is making a comeback as well too, and that again is an osteoinductive feature. Well, now metal has come around, and now with metal, in particular 3D additive technology, there's two types of metal technology. Destructive, take a block of metal, chop it away. It's called subtractive technology. But with additive technology, we can actually now create metal cages that have complex structures because we're building them from scratch. Welcome to Cage Rage 2.0, which is happening right now with the advent of metal. So metal can now be engineered, and we can now engineer porosity into the metals to now actually make them biologically active, which is different from the previous things where they were purely structural elements. And that's what's pretty exciting about what's going on. And this is a very early metal cage that came out in France that was actually chopped away. This was a subtractive process. They took a piece of metal and dug pores into it. Obviously a bit primitive because it doesn't take advantage of the complexity that you can develop with pores. On the right side here, you can see this is a 3D printed metal cage that was run in a lab. They were doing a rabbit model here by Bobbin. And what they were able to show was you can get bone growth right through the entire metal. And that really brought up the excitement of the newer cages that we have. And you can see all this literature and data looking at pore size, looking at the configuration of what's in metal cages to make them work. And it's an exciting time because for the first time, we can actually create nanostructures on metal to make it you can actually possibly make it osteoinductive as well as making very osteoconductive grafts out there. So can we actually engineer an osteoconductive synthetic implant? As a matter of fact, if you truly believe in this stuff, you may not even need a graft extender because it will do its own job. So look at this. Which one of these is bone? We've gotten pretty good. These are actually metal grafts. Only one of these is bone. I won't tell you which. But if you look at it and you're a bone cell, now imagine you're a bone cell and you're looking at this, they all look pretty, they look like pretty good homes, don't they? I mean, if you're a bone cell. And that's what we can do now with the newer technologies that are out because we can now leverage the porosity. And if you look at this, these aren't regular. If you even look at the artificial metal here, they have variability of pore sizes. They have variable surface structures. They all look a little bit different but similar at the same time. And that's what we can do. I love this video that shows, well, I can't image metal. This metal, the new metal we engineer with high porosity, you take an X-ray, you can see right through the thing. It's not your, well, I was going to say it's not your dad's cage, but it hasn't been that long. So anyway, it's not your senior partner's cage that he was used to. And this is sort of metal. And this is typical for the cages that are coming out right now, okay? If you look at this is a classic thing. PEEK is biologically bad, actually. The body doesn't like PEEK. But consistently over the data you've seen right now with these metal cages, metal is far more biologically compatible, and also it's got these inductive features that make bone want to grow there. Here's an example of a PEEK cage, which again, PEEK is not great, but you can actually put porosity features on it to have bone grow into it. On the right side, you can see there's nothing at the interface. There's actually an inflammatory response in the interface of green bone. Over here, bone is growing into the porous cage. Now, Bob had mentioned that in dental implants, they've gone a long way. They have, because dental implants, they just have to bind onto the surface. So surface characteristics are important. But if you actually look at what we need to do, we need bone to grow through the whole thing. So in the old days, when people would talk about porosity, this is like a previous thing, they would say past. Pore size and porosity was all they talked about. And this was from a TCP HA implant a while back. This is now what you see in a typical brochure for a metal cage, which talks about porosity, range of porosity, interconnectedness, porous architecture. This is good. I mean, you can imagine a future, though, where we have nano features built into the cage itself that we have printed that obviate the need for a graft extender. You may not have to use BMP. Microstructure with ideal porosity, making bones grow in that take advantage of pore size, variation, all these things. A macrostructure that has a modulus elasticity customized to the patient. Let's think in the future. You got a 3D printer in your OR, and you can print a cage exactly to your patient's specifications. Modulus elasticity at peak is close to bone. Whose bone? Average bone. It varies. Every single one of you has a slightly different modulus of elasticity. We could actually do that. And finally, the material properties, which are related to pore configuration, can provide radio transparency and optimal structural stability as well, too. So can we now, with the new advent of grafts, with 3D grafts, provide osteoconductivity and osteoinductivity? The answer to that is it's quite possible. So pores, what are they good for? True bone structure is very complicated, and it's commonly simplified to a concept of pores. But it's not as simple as pore size and permeability. There's shape, variability, interconnectedness, and tortuosity, but 3D engineered implants can now be designed for some or many of these pore features that can result in osteoconductive implants, and that's really, really exciting. Now, I'm going to finish with one set of pictures, but what's really interesting is every company selling you a 3D implant apparently thinks this is what bone looks like, and they have really cool graphics, but don't let that fool you, okay? Try to understand the science behind it. Bone is pretty much, every time I've seen, kind of bloody. It's a bloody mess, okay? Doesn't look like this, but it does come out with, we have some really cool graphics now with the new things that are coming out. All right, thank you very much. I hope that was helpful.